Section 4.3 is titled simply Area. And some of the things that we're going to have to think about is what we know about area of geometric figures that we've learned about before, in particular rectangle, and then how that will apply to any particular curve that we're working with. So the first shape that I want us to take a look at is a shape that's a cubic kind of a curve, right? The area of this region, and what I mean by this region, let me highlight it in so you can show you what I mean. If we start at this x value and we go to this x value and we fill in the area in between the curve down to the x-axis. Okay, so obviously this is not any of our standard geometric shapes, obviously, right? But we can approximate this by using rectangles. So what does that mean? Well, the idea is that we could subdivide this, say, into two equal lengths. Oops. Like this. Okay, so we sort of divided the x-axis up into two pieces. We could divide the x-axis again into two more pieces, so we have 4 rectangles. We could divide it into halves again and have more rectangles than that. So the width of all the rectangles on the bottom are the same because I'm dividing them evenly. Mine don't look very much the same, but pretend for a moment, okay, that this one and this one are the same length. That's what they're supposed to be. They're all the same. But the heights of these rectangles are different, right? So you can see that some of these rectangles are quite much taller than the others. And there's some discrepancy about what is the height. So like when I look at, say, this piece right here, how do I decide what the height of that rectangle is? Because it's not really a rectangle, is it? It's not. I mean, it's got that flat bottom on it, but it does not have a flat top. So what do we do for the height on that? Well, there's actually 3 different ways to determine the heights of those rectangles. Okay, there's 3 ways we're going to do it. The first way that we're going to do it is with left end points. All right, so we're going to draw the same picture that I just had. That is, I'm going to draw this subdivided, and I'm going to subdivide it into 4 because it's enough for you to see what's going on without it being too much to clutter up the diagram. So we're just going to divide it into 4. We call the first point x0, and then x1, x2, x3, and x4. This method uses left end points as the points where we take the height of the rectangles. So if you're looking at this rectangle that goes from x1 to x0 over here, which location has the height if we're using the left end point? The x0. This piece right here would be my height. So what would that look like? Well, it mean that I actually take this to be my rectangle. And I do that knowing that I just overestimated it, right? If I find the area inside of this rectangle right here, it is going to be more than the area under that curve. I've slightly overestimated it. So we're going to do the same thing for the next rectangle. Between x1 and x2, what will be the height? Where will it be determined? By the x1 value, right? And again, I have overestimated the height. How about between x2 and x3? x2. What happens on this one? I've actually underestimated my height, right? And then between x3 and x4? It'll be at x3, and again, I've underestimated my height. So this is not a bad example of it sort of balancing itself out, right? This one looks like you overestimated a couple of them, you underestimated a couple of them. It's probably going to give you a pretty accurate answer because visually it looks like we might have overestimated and underestimated by about the same amount, you know, all that kind of stuff. Some curves, they don't look like that. They don't look quite so nice and friendly and symmetric. This almost has a symmetric feel to it in the way I did my rectangles. All right, so what I want to show you then is I want to show you how we write the area of this shape, the area of these rectangles. So tell me what you remember about how to write the area of a rectangle. How do you find that? Right, you do length times width. Now I mentioned this on the previous slide, and we're going to mention it again. all the widths are the same if I've subdivided this evenly across, right? Okay, so what in the world is my width? Well, in general, the way that I find my width is I take, well, I'll find one for you in a minute. I call my width here delta x. Okay, so this length right here, if you remember from slope, delta just means change in. So the notation that we're going to use here is delta x, change in x. It's the length between a x1 and an x2, or an x3 and an x4. Or if we had 16 of them, an x13 and an x14, or whatever it is. Okay, it's the length between them. And if you take a look at this one in particular, we'll just do this in general for this one in particular, our delta x value is going to be x4 minus x1, right? The distance between the, x0. The distance between the first value, x0, the last value, x4, and then divided by 4, because I divided into 4 rectangles. So in general, delta x is going to be the first value minus the last value divided by however many rectangles you're working with. So if you're working with 10 rectangles, you divide by 10. Okay? So the width is the easy part. It's the height that's trickier because each of these heights are different, correct? Now I've sort of made a mark on each one of them, here and here and here and here. They're all marked, but notationally I don't have anything up here yet that makes any sense. So let's find the area of the first rectangle. So it's supposed to be the length, or the height, times the width. I know the width, we're calling it delta x. What's the height? How would I determine that? Well, it isn't the change in y, because I want the width of this rectangle right here. We're just looking at this rectangle only. How will the height be determined? It's the y value at whatever x0 is, right? What notation do you have for deciding what a y value is based on a specific x value? F of x. Okay, so far so good? So we would actually call this height on this first one f of x sub 0. And we would multiply it by the width, which is delta x. That's one rectangle. What about my second rectangle? What's its height? Right, f of x sub 1. And what's its width? Delta x. How about my third rectangle? What's the height of my third rectangle? And the same width, right? How about my fourth rectangle? F of x sub 3 times delta x. Okay. Notice there is no f of x sub 4 here, right? There isn't, because I didn't ever use that last determining value, that x sub 4 value, to actually give me any of the heights, right? It's part of the numbers in the display, it's part of my diagrams going on, but I'm not using it for any particular heights. All right, and what do you notice about every single term in this description? What do they have in them? Delta x. So what we're going to do is we're going to do a little bit of algebra to make our life a whole lot easier. We're going to factor that delta x out. And then we're going to notice that all we're left with is f of x0 plus f of x1 plus f of x2 plus f of x3. In other words, instead of multiplying 4 times, and then adding all 4 of those values together, I can add the 4 numbers together, the heights together, and multiply once, which means that I can shortcut the process. Does that make sense? This is what happens when we use the left endpoints. There is one more notation that I want you to be aware of, not because we necessarily use it all that much, but if you see it, you should be aware of what it's doing and how it relates to what we just learned in the last section. When we repeatedly add something together a whole bunch of times, That's a summation. This is the summation of f of x sub I, and in ours, it's from I equals 0 to 3, because we started at a subscript of 0 and stopped at a subscript of 3. And then we've multiplied this by delta x. You could put the delta x either after this description or before, it doesn't matter, because there's no sub I anywhere in what we're doing. We're not really going to write it like that at the bottom, but that is the relationship to what we were doing on the last section. Second way to do this, right endpoints. Okay, so this was left endpoints. What do you think is going to happen when we do right endpoints? How is this going to be different? You're going to use the right endpoints. So on my first rectangle, x0 to x1, and then I've got x2, x3, and x4. On my first rectangle on the far left, which endpoint am I going to use? This one right here, right? And I'm drawing the picture like this. This would be using the right endpoint of that first one. The second one I would be using x2. The third one x3. And the last one x4. Again, because of the symmetric feel to it, it looks like I'm doing just the same thing, but almost like flipped around or something like that. It's not going to work that way for every function. Notationally, it means that I'm going to use all the x sub 0 or x sub I values except for x sub 0, right? So when I'm writing down my area down here, we know we have the delta x. It's the width of every rectangle. We need to know what the 4 heights are. What's the height of the first rectangle? F of x sub 1. Height of the second rectangle? F of x sub 2. Third one? And the fourth one is f of x sub 4. You'll notice then we could write this again just so the notation starts to make sense together. It's a summation then from I equal 1 to 4 of f of x sub I. And again, you could put the delta x in the front like I did on this slide. You put it at the back like I did on the previous slide. All right. In general, right endpoints and left endpoints often overestimate or underestimate something. They're not usually just spot on. A better estimate is a midpoint estimate. So that's our third method. By the way, there are other methods. You can estimate these with trapezoids. Instead of using rectangles entirely, you can use trapezoids. That's another way to do this. We're going to stick with our rectangles because it leads into what we've got to do with the rest of this chapter very nicely. All right, so I'm going to mark the same places that I did before. I'm not going to write out a formula quite as nice and neat as I did on the previous ones because notationally it just really looks messy. I'd like for you to notice I still have 4 rectangles, right? Okay? But what I do on this method is I locate the place between these x values, and I sort of come up here and I notice that the height then, there is an x, all right, there is a point at that x value for the height. Like this, and those blue dots are going to now be my height. So somehow it sort of splits apart the rectangle. I still have 4 rectangles. I don't have 8 rectangles, but it splits this differently, like so. If you compare this to the other picture, I'm off by less because I've sort of balanced out the overage and the underage. That's not even a word, is it? Underage? Overage is a word. There should be a word that's underage, but that doesn't sound right at all. The amount that I'm over and the amount that I'm under in every rectangle has been sort of balanced. Do you see that? On each individual rectangle. And so as a general statement overall, that means that my estimate is usually, now I'm not going to say point blank all the time forever and always, but usually I end up with a better estimate by doing it this way. There are still 4 rectangles, but the heights are found at the midpoint of each of those x sub 1 to x sub 2 values, the midpoints between them. All right, so we're going to do an example, all right? We're going to do an example where we find all 3 of these methods, and we've got a function and all that good stuff. We will probably find it helpful to draw a picture. You don't have to, but you could. This one says, approximate the area under the curve on the given interval using n rectangles. Okay, n equals 4 in this problem. And then it says using left endpoints, midpoints, and right endpoints. All right, you ready? Yeah? All right. So we're going to start with A, left endpoints first. Actually, let me draw a picture just for the sake of having done it so that we're all visually on the same page of what this looks like. All right, 2x squared plus 5. What shape is that? Good. It's a parabola, opening upward, right? And it's been shifted up how many units? 5. So its y-intercept is somewhere up here. Whoops. Like this. And I'm only drawing this half of it. Why? Why do I not need to draw the other half? Yeah, the interval is only going from 0 to 2. So here's 1, here's 2. So my interval is something like this. And I'm supposed to be going from here to here. And I want the area under this curve. Okay, everybody good so far? Okay, fantastic. Alrighty then, so I need to find 4 rectangles. I've already drawn in 2. I need to draw in 2 more. So I'm going to split these intervals in half. And what will the x values be when I split them? Yeah, 0.5 or 1 over 2 and 1.5 or 3 over 2. So I've got x interval or x values of 0.5, 1, 1.52. Is everybody good with that? Okay, this is the picture that I need to be thinking about, whether I draw it or not. It's the good picture to think about in order to find the left endpoint, the right endpoint, and the midpoint areas. So we're going to start with the left endpoint ones. Now on all of these formulas, I've got this delta x business going on, and then I've got a bunch of f sub x kind of values going on, right? And it's going to start at f of x sub something and stop at another one. These are not the same f of x values. But I've got a bunch of f sub x's. This is what I'm doing. All right, so what is the delta x in this problem? How far apart are my x values? They're 0.5. And you can usually see that if you've drawn your picture very quickly. Now I need to determine this with my left endpoints. So what is the first left endpoint? It's 0. So the first x value that I'm finding is at x equals 0. What's the second one? F of 0.5. The third one? F of 1. The fourth one? F of 1.5. And we do not have an f of 2, correct? Because that is not a left endpoint. And the beauty of this right here is that your calculator is very good at finding this. So I want to give you some tools in your calculator. You may not know how to do this. So first thing I'd like for you to do is I'd like for you to write this equation. What was it? 2x squared plus 5 and y1. So in your calculator, I want you to do y1 equals 2x squared plus 5. Okay, is everybody good with that? All right, so one way to do this is to use your table and to go in and just plug in 0, 0.5, 1, and 1.5, right? Let's do that. We'll do that one first. Okay, so what do you get at 0? That's 5. What do you get at 0.5? 5. Okay, and at 1? 7.5? 7. Oh, 7, okay. And 1.5? 9.5. And then back in the regular screen of your calculator, you can add those 4 values together, multiply by 0.5, and you're done. So what does that give you? Do we get 13.5? Okay, now I want to show you how you can jump from here down to here and just avoid the step where you actually found the 4 values in particular. So why might that be helpful? Well, this problem was pretty nice because they were either whole numbers or 0.5s. What happens if you had ugly decimal expansions and you had to keep like 4 or 5 decimal points to make sure you didn't round error and stuff like that? That wouldn't be very friendly. What if you had n equal to 16 rectangles? Very unfriendly, right? So what could we do to make this process easier? Well, in your calculator screen, regular screen, you still have to put in y1 equals 2x squared plus 5, okay? But in the regular screen, what you can do is you can tell your calculator, and I'll show you how to get this, y1 of 0 plus y1 of 0.5 plus y1 of 1 plus y1 of 1.5. You can tell your calculator to do that. In other words, you don't need to find the individual values and then add them. Your calculator can do that all in one step. That's pretty cool, right? It is. So let me show you how you do that. Okay, back in your regular screen, your calculator, so exit out of the graphing screen, you should be in a regular screen. There's a button that says VARs. Do you guys find it? Okay, and the first one says function. So select function. So hit enter on number 1.
It's a window.
Oh, it needs to be over to YVARs. I'm sorry. Over to YVARs. Okay, so you hit VARs, and then you hit function, and then you go up to YVARs. Do you see the Y1 now? Does everybody see the Y1 there? Hit enter. And then you can put parentheses, 0 in parentheses, plus VARs, over to YVARs, function Y1, and you can put in 0.5. Does anybody need any calculator help? Are you getting it, Stephen? You okay, Cooper? Okay. This is handy, handy, handy kind of thing because it's going to save you time and probably save you some accuracy. And then once you get to the end of that, putting in y1 of 1.5, you hit enter. And then you can hit times 0.5, and you should get 13.5. Did you? I got a thumbs up from Jacob. Did you get it, Kenzie? Good. Let me have a parenthesis issue. Let me see. Oh, you've changed it every single time to do y1, y2, y3, y4. They're all y1s.
Oh.
They need to all say y1.
That makes sense.
Okay, let's try the next one. We're going to use that feature instead of finding them individually. We're going to do the right endpoint. Whoops. Okay, so part B is to do the right endpoint. So in terms of our picture, we're going to find out that we have, well, I guess this is part C. I'm doing them out of order. I still want to do the right endpoint next. So we'll do C first. Okay, so we've got still the same delta x value, right? Delta x will be the same. And I have my 4 f sub x values that I need to put in. You don't have to write this step. However, you do need to write the next one. You do need to write out for me that you are going to take 0.5 and that you are going to multiply it by some f of x values. What is the right endpoint of the first or the leftmost rectangle? 0.5. My first right endpoint is at 0.5. What's my second right endpoint at? 1. And then 1.5. Don't get carried away too. I'm going to show you another cool feature of your calculator. You're going to love it in just a second. And then f of 2, right? Okay. Now, as friendly as that last process was, Wouldn't it be even friendlier if you didn't have to enter every single one of those all over again? It would. Notice, what's the difference between the expansion here, 0.5, f of 0, f of 0.5, all of that, and the expansion over here? What's different? Just one number, right? F of 0 on the first one, and there's an f of 2 on the second one. Are you guys with me? That's the only difference. So in your calculator, I want you to okay, so you're back on your regular screen. You already hit the enter button. You already found the 13.5 before. I want you to hit second, enter, second, and then the enter button. That should pull up the previous line of text that you had. And if you hit second, enter a second time, it'll pull up the line where you multiplied everything out, or you added everything out, rather. And then all you have to do is to change the first f of 0 and make it say f of 2. Did everybody follow that? That was a lot of details on that step. So really what your calculator is now going to say is it's not going to actually look like this. It's going to look like y1 of 2 plus y1 of 0.5 plus y1 of 1 plus y1 of 1.5. And the order of it's going to look different. And then you can hit times 0.5 when you're done. And you should end up with a very close value to what you had before, but it will be different. What is it? 17.5? Yes? Very good. All right, let's do midpoints. So this is part B that I skipped because the first one and the last one are far more related in terms of the computation. Okay, so for the midpoints, I still need to have that 0.5 out in front. But my midpoint values are not any of the values I've used so far. What is the midpoint for the first rectangle? It is 0.25. You got it. So the first one will be f of 0.25. What is the midpoint of the second rectangle? It is. It's 0.75. How about the midpoint of the third rectangle? 1.25. Good. And the midpoint of the fourth rectangle? Halfway between 1.5 and 2? 1.75. Now you can use that second entry feature if you'd like we did on the last one, and change all the data values on the inside. That's okay. Or you can enter it from scratch. It's probably not going to take you any longer either way, because you're going to have to do a lot of inserting numbers, because these are 2 decimals long and the other ones were only 1 or not at all. So it might take it a little bit longer to do that. But we can jump straight from here to the answer. And what do you get? Any questions on that one? Did we all get 15.25? I guess I only listened to actually Alexa. Yeah? All right.